All right, 7.5, model data with logarithmic functions. We're going to look at logarithmic regressions. Logarithm, again, what is that? It is actually closely related to an exponential function. It is mathematically the inverse of an exponential function. Okay, and if we took pre-calc 12, we would do things like this. There's an exponential function. Function in terms of x. Let's call this thing 10 to the power of x. And we should know the shape of this exponential function. Here it looks like the y-intercept is 1. It's 10 to the power of x. Of course, it's an exponential growth. If I take the inverse of that, which in pre-calc we know is a reflection over this y equals x line, what I get is something that looks like that. And that is a logarithmic function. A times log base 10 of x, where a has got to be something positive. This is increasing, just like the exponential one is increasing. Okay, as x gets bigger and bigger and bigger, y gets bigger and bigger and bigger. That's increasing. The other exponential function we know is a shape that looks like that, where f of x, here I know the value is something less than 1. This is 10 to the power of x. This has to be a proper fraction, technically between 0 and 1. Okay, not an improper fraction, but 0.5, you should know that's the shape that thing looks. If I take the inverse of that, what I get is something that looks like that. Okay? So visually, does that kind of look like, if that was a mirror on that dotted line, do they look like they're symmetrical about that point? Okay, maybe not perfectly, but close enough. That is also f of x, not y, function of x, same thing, in the form a log base 10 of x, but here a is less than 0. A is decreasing. Or sorry, a is negative. The function is decreasing. Okay, so you got to know this. You know the shape of an exponential function. You got to know the shape. A log function will look like that. If a is positive, it'll look like this. If a is negative. Characteristics. We've done this for quite a while now, so I shouldn't need to point this out, but what's the domain and range of this thing? I'm not going to write it down, but you see that this is an asymptote here, the y-axis now. It was the x-axis for an exponential function, but this thing was inverted, so now it's the y-axis, so it looks like the domain is everything greater than 0. Goes out that way forever and ever and ever. The range now is all real. Okay? Goes down, goes up, so y is all real numbers. All right, same thing with this guy. Right? Y is all real, and x is every value greater than 0. Never, 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 ever touches this line. It's never equal to 0. That's all the values greater than it. And behavior, okay, pretty straightforward, not even going to talk about it. So log 10, that's the only thing that this calculator gives you. You notice the 10x button is right underneath it because they're related. They're inverse functions. That's why they put them close together on this calculator when they designed and built it. Log base 10 is the only one you can have on your calculator. Again, in pre-calc, we do all sorts of different bases. Base 2, base 4, base whatever. The one in particular we want to look at is log with a base of e And in that case, what we get is log base e of x. That's something special. This is a special number. We could do a whole course on that number. It's Euler's number. But all we're concerned about knowing is this is called a natural logarithm. And that's what our function is going to give us when we get a regression function with this, okay? So, natural logarithm. Like I say, we can do a whole course on this. We're just doing this for like 2 days. So, our calculator is going to give us a regression function that looks like that, okay? A is some number, B is some number, natural logarithm of x. Example. I'm in red. Let's go back to blue. Carbon dating. So we're going to test some stuff we find in the ground, usually bones, and see how much carbon-14 is left. All right, you've seen this before, probably in Science 10. So I take one sample and I measure it, and it tells me it's got 56% of carbon-14 left. And I determine that's 4,768 years old based on some formula. Something else gives me this. All right, something else gives me that. I test something else. It's only 9%, which means it's probably older, right? Because the carbon percent goes down over time. So what kind of a graph is that? Well, think, or quickly plot. And this isn't in the right order you probably want. I just want to show you it doesn't matter. This is only 9 years. It goes up to 70, okay? 9 is 20,000. Let's call that 20. Doesn't like to write near the edge. 20,000 up there, all right? The next biggest one's 37. That's 8,000, a little less than half. About 4 times that. That's down there, close enough. 51's 5,000. Over there. 56 is over here. 70 is only 2,000. That's way out there. That's 20. I want 1/10 of it. Okay, so just a 10-second graph looks like that. Does that look like one of these guys up here? Yeah, it looks like that. So now I kind of think, all right, that's a log function. That's what I want to try to get a graph of in my calculator. So what is the regression function for this? Okay, this thing's factory reset to 0. It's a computer program. It's not a real calculator. Actually, I take that back. I already used it today. But all right, when I turn this on, usually the window is -10 to 10. What do I want this window to be? Well, I go up to 70. This is going to be my x. That's going to be list 1. Okay, so 0 to 150. Well, let's just go to 100. I may ask a question where you got to go farther than 70. So don't just put 70. At least add a little bit in there. All right, years. I got to go to 20,000 here. So let's actually go to maybe 40,000, because again, you're going to get some extrapolation questions where we got to plot these points beyond where the graph ends, okay? So I want to have a little room in there for my calculator. Put the data in. Actually, like backtrack. Second function, I want to clear all the lists. Second function, memory, number 4. Clear the lists. Let's get rid of all the other data that's in there first, okay? Then I want to go to data. Edit, enter, over to list 1. I want to put these numbers in. Again, it doesn't matter what order. Calculator knows how to plot points. 9 and 70, okay? Go over to list 2. 4, 7, 6, 8, 5, 5, 5, 6, 8, 2, 8, 2, 1, 4, 9, 1, 9, 9, 6, 0, and lastly 29, 20. Double check you put it in properly, okay? If you're missing a point or one of these doesn't line up, if there's something missing, the calculator won't do it. Double check that before you start playing around with everything else. Okay, what's the function for this? Stat, calc, okay? I don't want quadratic regression, don't want cubic, quartic. I know this thing looks like natural logarithm, okay? That's the ones we were doing yesterday, exponential. I want ln regression, natural logarithm regression. So go down to 9, press enter, or just hit 9. And this stuff, I have it in list 1, comma, list 2, comma, and then I want to stuff it into the y equals so it'll graph the line. So go to vars, y vars, function, y1, yes please, enter, it's thinking. Okay, there's the equation. So let's write that. 38, again, that's in the form y is a plus b ln of x. Okay, a is 38, 212, b is minus 8307. Okay, does that make sense? A is less than 0 if it makes this shape. Okay, 8307 ln x. So that's the function. All right, graph. There's the points I plotted in, and because I did the vars thing and stuffed it in y equals, it's given me the line. So if I'm asking you if a sample had 85% of C14 left, well, what's the question? How old is it? All right, well, then I'm going to hit trace, and you got to know what the y and the x equals. The x was the percent left, right? That's the independent variable. The age is determined by how much carbon-14 was left. I want 85%, so I got to scroll the other way. And notice, if I do this, it only goes to the points. What you actually have to do after you hit trace is hit the up arrow. That releases it, so I can scroll along the whole line and extrapolate, interpolate. So I can go way over to, going the wrong way, 85, or, because it's x I want to do, just put in 85. Enter. Bingo. 85% carbon left. It's only 1,306 years old. And again, that's because of my graph and the way I scaled it. It's kind of hard to see because that's way down here, right? So there's the answer. If I'm asking you a question of course, if I give you the year and say, what's the percent carbon left? Well, we can just scroll along until you find it. Let's say it's 3,000 years. That's actually pretty close. Let's say 4,000 years. I already got one pretty close. All right, well, every dot I hit, it goes 3825, 3967. That's probably the closest. That's a pretty big jump, right? So it's between 60.6% and 61.7%. If you're looking for an approximate answer, I'm probably going to take it right in between those two. Okay, it's about 61%. If you need something exact, then you're going to go down in here and put in a line right at 4,000 and plot it, and then you can trace along that line, okay, until you come right up to that point exactly. Like, now I'm on that line. Okay, I'm going to go over until it crosses over the other line. Of course, there is a function in here to do the intersection, 5, between the first curve and the second curve, and then it'll give me the exact answer. Okay, at exactly 4,000, that's 61.46%. But again, if we just want to do approximate, we can just trace it. Okay, so that should be it. Again, the instructions on how to do that was in the last lesson. Questions you need to do are 495, start with 6. Okay, I have these in a specific order. Then do 5, then do 9, but 9 I want you to do 2 days? No, 2 ways. I want you to do that 2 different ways. Because this is an inverse of an exponential function. You could plot this upside down, okay? And if you put this as L1 and you put that as L2 and do an exponential, it'll look like that. If you're answering the questions, you'll get the same answers, but of course it's going to give you a different function. So 9, I want you to do that 2 different ways. Because sometimes when you're looking at the data, it's hard to know which is the independent and the dependent variable based on if it's exponential or logarithmic. So first do exponential regression with L1, we'll take it as X months, and L2 years, okay? And then do a natural log regression with the backwards. Do it backwards. L1 years, it's actually, I mean, this should be the independent variable as you've been taught, right? All right, so do it 2 ways. You should get the same answers. Of course, the graphs are going to look completely different, but it's all good practice.